Today, we will look at a new topic called Combinatorics under our word problem series. In this chapter, we will look at the fundamental counting principle, simple factorials, anagrams, permutation and combination, and multiple arrangements. Now, we will begin by looking at fundamental counting principle. Most problems you will encounter under this section will test your ability to be able to count. Now, although counting may seem to be a simple concept, problems about counting can be complex. Combinatorics is a subfield under mathematics to help deal with counting problems. Now, fundamental counting principle states that if there are X ways of making decision A and Y ways of making decision B, then multiply the number of ways to make each individual decision. That's X times Y to find the number of ways to make all the decisions. Now, to understand this principle, imagine that you are making a sandwich. You will choose one type of bread out of two. Let's say butter bread. Okay. And sugar bread. And you will also choose one type of filling out of three types. Okay, so we have fried egg, peanut butter, or salad. So essentially, out of two bread options, you have to choose one. That's butter bread and sugar bread. Out of three fillings, fried egg, peanut butter, and salad, you have to choose one. Now, how many different kinds of sandwiches can you make? Now, we can list all the possibilities. Okay. Now, we can have, I'll use BB for butter bread. Okay. And SB for sugar bread. You can have butter bread with what? Fried egg. You can also have the butter bread with what? Peanut butter. And you can also have the butter bread with what? Salad. We can also decide to go with sugar bread with what? Fried eggs, or sugar bread with what? Peanut butter, or sugar bread with what? Salad. So here you see that there are 6 possibilities, or 6 possible sandwiches we can make. Now, instead of listing all the possible sandwiches we can make, you can simply multiply the number of bread choices, which is what? 2, by the number of what? Filling choices. Okay, which is what? 3. As directed by what? The fundamental counting principle. Okay, so that 2 times 3 is what? 6 possible what? Sandwiches. Now, try your hands on this question. Now we'll turn our attention to simple factorials. Now, the number of ways of putting n distinct objects in order if there are no restrictions is n factorial, okay, which is represented by this n with this symbol. Now, the term n factorial refers to the product of all the positive integers from 1 through n inclusive, okay, where n factorial is this. So you have n and then n minus 1 and then n minus 2 all the way to, to 1. We can demonstrate an example where if you have 4 factorial is what? 4 times 3 times 2 times 1. We can also look at what? 5 factorial, which is what? 5 times 4 times 3 times 2 times 1. 6 factorial is what? 6 times 5 times 4 times 3 times 2 times 1. Now, it is recommended that you memorize the factorials through to 6 factorial, okay, so that on the exam you are, able to quickly compute, some of these products, okay. 6 times 5 times 4 times 3. It's easier if you already have them at hand. Now here it says, how many different ways can 4 peoples be arranged in 4 fixed chairs? Now here it's simply 4 factorial, okay, so 4 times 3 times 2 times 1, which is 24. Now, we can use the slot method to explain why this is the case. Now, in the case of this particular example, okay, where we are arranging 4 peoples on 4 fixtures, we can decide that slot, or each slot represents a chair. So if we place any one of the 4 peoples on the first chair, okay, there are what? 4 possible people who can sit on this chair. Immediately one person sits down, we have 3 people left. For the next 3 people, there are only 3 choices. And for the next available seat, there are only 3 peoples. And if one person sits down, then it means the next seat, there are only 2 people left. Okay. And so looking at this slots as chairs or chairs as slots makes it a bit easier for us to understand the concept of factorial and how we can use it to count. Now, for the last slot, since you only have one person, one slot or one chair left, you put the last person on that last chair. Now, you multiply together all those separate choices, as we have seen, directed by the fundamental counting principle. And then you arrive at what? 24. Now here we have this example which says that if Ghana decides to create a 4-digit postal code system to assign to each town, the first question is, how many number of possible postal codes can be created? Number 2, how many number of possible postal codes can be created such that the first digit is non-zero? Number 3, how many number of possible postal codes can be created such that the first digit is non-zero and none of the digits is repeated? So here we will look at all the 3 questions and see what we get in terms of our solutions. Now here let us draw what 4 slots. Okay. Now remember that when it comes to the number of digits we'll be dealing with, we'll have what 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So there are 10 digits in all. So for the first question, it says how many number of possible postal codes can be created. So if you look at the 10 digits, here there are 10 possible numbers that can go here. First slot. Now for the second slot, there are also 10 number of what digits that can go for the second slot as well. Now for this particular slot, which is what the third slot, there are also 10 number of digits that can go here. For this slot, this last slot, there are also what 10 digits that can go here. So in all, here we've made how many decisions? 4 decisions. Multiply all those 4 decisions and then you get what? 10,000, total number of postal codes. Then we get 10,000 total number of what? Postal codes. Now number 2. Four slots again. Now, how many number of possible postal codes can be created such that the first digit is non-zero? So here, if you consider this first slot, you realize that because 0 cannot be part, we only have what? 9 possible choices for the first slot. And then the rest will be what? 10. Okay, multiply all the choices. And then you have what? 9,000 different postal codes. Now, number 3. How many number of possible postal codes can be created such that the first digit is non-zero and none of the digits is repeated? So here, this one is a bit tricky, so you have to be careful. Again, we have what? 4 slots. And the first slot, the first digit is non-zero. Okay, so here is non-zero. So we have what? If we take out 0, we have what? 9 digits left. 9. Now here, it could have been 10, but now we have this restriction which says that what? None of the digits is repeated. So let's assume if we pick 1 here, we cannot pick 1 here again. Okay, so here we are restricted to, let's assume we picked 1, but now 0 can come in. So once we pick 1, we have what? 9 options to choose from. 9 choices. And then let's assume that we pick 0 and 1. Now all of a sudden we have what? 8, because we cannot repeat. And then if we pick 1, 2, 3, now we have what? 7. Okay, so multiply all these different choices. And then what do we have? We have 4,536. So this is just to demonstrate to you how you can use the slot method to solve, simple factorial questions or combinatorics questions. Now try your hands on this example which says Jenny bought a bookshelf and decided to place 5 different books in the bookshelf. In how many different orders can she arrange the books? Now here we will turn attention to anagrams. Now, an anagram is a rearrangement of the letters in a word or phrase. Now, for instance, the word earth is an anagram of the word heart. And so is the gibberish word reta. Now if you look at this word heart, we've just rearranged it to get earth, and we've rearranged it to get reta. It doesn't matter. Earth makes sense. We rearranged heart to get earth, which is a proper word, but reta is gibberish. Now when we are dealing with anagrams, when you are asked to find a possible number of ways you can arrange a word, it doesn't matter if the word makes sense or not, whether it's gibberish or it's a proper word. So don't be too bothered about that. Now let's look at this example. It says how many different anagrams are possible for the word exam. Now bear in mind that we are using factorials to solve these questions. And so here you have these slots. Now here you have four distinct letters. If you decide to put one of the letters here, it means, because the letters do not repeat, it means you have three choices left. So you have three choices which can go into the next slot. Now if two slots are gone, now you have two letters for this third slot. So you put 2 here, and then finally you put the last slot, and then we multiply all our choices. And this is 4 factorial, which is 24. So try this. In how many different ways can the letter scholar be arranged? Now try your hands on questions under problem set 1. Now here we turn our attention to permutation. Now factorials required us to have the same number of pupils as chairs to sit on. But what happens if there are not enough chairs for everyone? Now permutations are used when you select objects and you care about the order of arrangements. Now we have this nice formula here, that really makes it very simple to solve permutation questions. Some books try to use a grade, and the anagram grade. I kind of feel that for the purposes of this exam, the formula is cute, it's faster, you know it, you plug your numbers in, you are gone. You don't have to overthink, you don't have to overdo the stuff, and it helps us to be able to move quickly. Now here in this formula we have this NPR, which is permutation. This one is N is the total number of objects, and then R is the number of objects selected. So for instance, we have this example which says in a musical chairs game there are 7 pupils and 3 chairs. How many different seating arrangements are possible? So here straight away you know that N is 7 and R is 3. And so for the formula you have 7p3 is equal to 7 factorial all over 7 minus 3 factorial. 7 minus 3 factorial. Okay, now let's bring this here down here. So here you have 7 factorial. 7 minus 3 factorial is what? 4 factorial. This is what? 7 times 6 times 5 times 4 times 3 times 2 times 1 all over what? 4 times what? 3 times 2 times 1. This one will cancel this side. And then you have what? 7 times 6 times 5, which is equal to what? 210. So essentially, there are 210 different seating arrangements that are what? Possible. So here, typically, when you see permutation questions, okay, they typically have the word arrangement, possible ways of arranging, the order. It cares about the order of what? Things. So whereas what we are going to look at next, which is combination, doesn't care about arrangement. Permutation cares about arrangement. So if you have what? Let's say A, B, C, and you are told to see the different number of ways you can, pick two letters out of A, B, C. Okay, A, B will be different from B, A in terms of permutation, but under combination, it won't matter. A, B, and B, A will be the same. Okay, and that's the difference. So always take note, that permutation questions usually have the word arrangement, the order of things. Okay. Now let us move on and take a look at what we have here, which is what? Combination. Okay. Now, as we have already seen, permutations are used when you select objects and care about their order, like the order of pupils on the chair, and the stuff that we've already seen. Now, however, in combination problems, we do not care about the order. We just care about picking people or picking objects or picking things. Okay. Now, here we have another formula for combination, which is this: n factorial divided by n minus r factorial times r factorial, where n is the total number of objects and r is the number of objects selected. Now let us jump into this example, which says if 3 out of 7 pupils are selected for a musical contest, how many different combination of pupils can be selected? Okay, so here we know what n is. N is what? 7. R is what? 3. Okay, so 7C3 is equal to 7 factorial. Now we have 7 minus 3 factorial, and then what? 3 factorial. Okay, so here we know that 7 factorial, and then here 7 minus 3 is what? 4 factorial, and then you have what? 3 times 3 factorial. And then this one is what? 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by what? 4 times what? 3 times 2 times 1 times 3 times 2 times 1. So here, remember, this one will cancel out this one. This is 3 times 2, which is 6. This one will cancel this one. And then you have what? 7 times 5, which is what? 35. Now, this question is similar to the question we solved under permutation. The only difference is that we cared about the order of things under permutation, whereas here we don't care about the order of things. We're just selecting 3 out of 7. Now, so you realize that under permutation, the number of, with similar pupils, 7 people, and we are selecting 3, but because we cared about the order of things, the order of arrangements, we had what? 210 possible arrangements. Whereas under combinations, we are just picking people. We don't care about the order of things, and so we had what? 35 number of people, different combination of people that can be what? Selected. Now try your hands on this particular what? Example. Now here, under multiple arrangements, you are likely to encounter multiple selection or arrangement problems in one question. Okay, let us try our hands on this example to demonstrate how questions under this particular section are framed. Now here it says 3 boys out of 7 and 3 girls out of 6 will be chosen to form a music band without competing for spots. In how many different ways can the band be formed? So here, remember that we are choosing what? 3 boys out of 7, and we are also choosing 3 girls out of 6. It's like 2 different, selection problems all put in what? One question. So here we have 2 choices to make. 3 boys out of 7 and 3 girls out of 6. And so here it's a purely combination question. We don't care about the order. All we care about is, the people that we are picking. And so we know that out of the boys, there are what? A total of 7 boys. We are picking what? 3, put boys here. And then girls. And then out of the girls, there are a total of what? 6 girls, and then we are picking what? 3. And so here, clearly we know that 7 combination what? 3 is equal to what? 7 factorial, all divided by what? 4 factorial times 3 factorial. Okay. And then this one is what? 7 times 6 times 5 times 4 times 3 times 2 times 1 all over what? 4 times 3 times 2 times 1 times 3 times 2 times 1. This one will cancel out. This one will cancel this 6, and then you have what? 35. And then this one here, you have what? 6 combination 3 is equal to 6 factorial all over what? 6 minus 3 is what? 3 factorial, and then times what? 3 factorial. Then here you have what? 6 times 5 times 4 times 3 times 2 times 1, all divided by what? 3 times 2 times 1 times 3 times 2 times 1. This one will cancel this one. 3 times 2 is 6. It will cancel what? This 6. Then you have what? 5 times 4, which is what? 20. Now we have this decision for the what? The boys, and that decision for the girls. Multiply these two together as the fundamental counting principle says to arrive at what? Your solution. So 35 times 20, which is what? 700. Now try your hands on questions under problem set 2. This brings us to the end of Combinatorics under the word problem series. See you in the next video.